So far, we've explored a number of wave properties, including the superposition or interference when waves combine, as well as the reflection and transmission at a boundary of different media. In this video, we will investigate how the superposition and reflection principles can be applied to characterize how the motion of sinusoidal waves under certain conditions can give rise to what is known as standing waves. The type of waves, for example, that are found in string musical instruments or wind instruments such as the flute or the clarinet. If a stretched string is clamped at one end, an incoming wave will be reflected from the fixed end, thus creating a second wave that is inverted and moving in the opposite direction. There will be two waves of the same amplitude, frequency, and wavelength. The incident wave and the reflected waves will combine according to the superposition principle. When the two waves combine, it does not look like that the resultant wave moves. Hence, this wave is called a standing wave. A standing wave is a stationary vibration pattern formed by the superposition of two waves of the same frequency traveling in opposite directions. In this animation, we separate the two waves for a better visualization of the superposition. At some time during the superposition, the two waves are in phase with each other, producing constructive interference, and the resultant standing wave has an amplitude that is twice the height of the amplitude of the individual waves. More specifically, the resultant amplitude is the sum of the individual amplitudes. At other times, however, the two waves are out of phase with each other by exactly half a wavelength apart, and the peak of one wave coincides with the trough of another. This produces destructive interference, and both waves cancel each other out. There are points along the wave which oscillate at a maximum amplitude. These points are called antinodes. Halfway between the antinodes are points that do not oscillate at all and have zero amplitude. These points are called nodes. Every other point along the string will oscillate at some different amplitude between zero and the maximum. Assuming positive direction being towards the right, then the wave functions for the incident and reflected waves are given by y1 being the amplitude multiplied by the sine of kx minus omega t, and y2 being the amplitude multiplied by the sine of kx plus omega t, where k is the wave number given by 2 pi divided by the wavelength, and omega is the angular frequency given by 2 pi times the frequency. The algebraic sum of the two waves is y1 plus y2. Using the trigonometric identity, sine of a plus or minus b is equal to sine a cos b plus or minus of cos a sine b, then what is the resultant waveform simplified to? When y1 and y2 are added together using the trig identity, the result is that the standing wave is equal to 2 times the amplitude multiplied by the sine of kx multiplied by the cosine of omega t. The amplitude of a wave particle at a position x is given by the position-dependent part of the wave equation, that is, 2a of sine kx. It can be seen that the maximum amplitude has a value of 2a, which occurs when the term sine of kx becomes equal to plus or minus 1. Points with the coordinates that satisfy the condition sine of kx being plus or minus 1 are effectively the points that will oscillate at the maximum amplitude, or are the antinodes. Antinodes therefore will occur when kx is equal to 90 degrees, or pi on 2, 270 degrees, or 3 pi on 2, 450 degrees, or 5 pi on 2, etc. Since the wave number is equal to 2 pi over lambda, then the antinodes will occur at the following positions on the x-axis, at x being pi on 4, 3 pi on 4, 5 pi on 4, 7 pi on 4, and so on. The positions of the antinodes can then be generalized as n pi on 4, where n is an odd number integer starting with 1, e.g. n can be 1, 3, 5, 7, etc. Note that adjacent antinodes are separated by distance equal to half of a wavelength. At which x coordinates do you expect to see nodes? Sine kx will be 0 when kx is equal to 0, pi, 2 pi, 3 pi, 4 pi, etc. Given that k, the wave number, is equal to 2 pi on lambda, then kx will be 0 when x is equal to 0, pi on 2, pi, 3 pi on 2, 2 pi, etc. So this can be generalized as n pi over 2, where n is an integer. The distance between two adjacent nodes is also equal to half of a wavelength. So what is the distance between a node and an adjacent antinode? A standing wave is a stationary vibration pattern formed by the superposition of the incident and reflected traveling waves that have the same frequency but move in the opposite direction. The wave function for a standing wave is given by a sine of kx times the cosine of omega t, where a is the amplitude of the standing wave, k is the wave number, and omega is the angular frequency. Standing waves appear to consist of points that oscillate at variable amplitude. There are points known as nodes that do not vibrate and therefore have zero amplitude. Antinodes, on the other hand, are points that can oscillate to the maximum amplitude. Nodes will appear at coordinates where x is equal to n lambda on 2, where n is a positive integer starting at 0 and lambda is the wavelength. Antinodes will appear at coordinates where x is equal to n lambda on 4, where n is an odd integer starting at 1.